So, this section, we're going to be looking at some applications of the absolute extrema that we talked about in the last section. So the math is basically the same as what we did in that section. Setting up the math may be a little bit trickier at first. I know word problems sometimes are intimidating, so we'll just do a few word problems. Not really much in the way of theory or setting this up. We're just going to do some word problems, and you will see how this works. So nothing too bad, but I do know that word problems can sometimes be a little bit intimidating. So this first example, we have find two non-negative numbers, x and y, so that x plus 3y equals 30 and x squared y is maximized. So this is the function that we need to pay attention to, that we're are primarily interested in. So let's call this m, since we want to maximize it. M equals x squared y. And of course, we don't really know much about functions in two variables. So we also have this constraint, x plus 3y equals 30. And so what we can do, you could solve this for either of these variables and plug it in. I probably would not suggest plugging y in for x because you square it. So let's solve this equation for x. Or sorry, let's solve it for y. So y equals negative 1/3 x plus 10. And now let's substitute this in, and we get m equals x squared times negative 1/3 x plus 10. Let's distribute our x squared, so we get negative 1/3 x squared plus, or x cubed rather, plus 10x squared. And now, of course, when we talk about maximizing something, we are going to talk about, or we're going to need to take the derivative. And of course, like I've said in other videos in this part of the course, eventually you're going to take the derivative at some point in every problem. So we get negative x squared plus 20x. And then we set this equal to 0. And we can factor out a negative x or factor out an x either way. And so we get that x equals 0 and x equals 20. Now, the other thing is, if you remember from the last video on absolute extrema, we also, when we're finding the absolute maximum or absolute minimum, we also have to consider the endpoints. So what are the endpoints of this? Like, what's the domain of this problem? Well, we know that x and y are non-negative, and we know that x plus 3y equals 30. So that means that x cannot be less than 0. Could be equal to 0 because 0 is non-negative. But it also cannot be more than 30 because y is non-negative. So the best that we could do with y is make it 0, but then x cannot be greater than 30. So x is always going to be between 0 and 30. And then we have this critical number 20. So using our extreme value theorem, we could find, we'll say m, or let's just do this. We'll say x is 0, x is 20, or x is 30. So our maximum has to occur at one of these. And if x is 0, I guess we also need y. If x is 0, so plug that into here. So if x is 0, y is 10. If x is 20, then y is going to be 10 minus 20/3, so that would be 10/3. And then if x is 30, then y is going to be 0. Okay, so now we can find m. So m of course is x squared y. So 0 squared times 0 would be 0. 20 squared times 10/3 would be 4,000 over 3,000 thirds, or 1,333.3 repeating. And if y is 0, then x squared plus, or x squared y is 0. So here we have our maximum, and this happens when x is 20 and y is 10/3. So we're just doing the same things we did in the last section. The main point with these is getting these equations set up, and the one that you want to maximize or minimize is going to be the one that you're going to take the derivative of. Before you can take the derivative, you need to get it as a function in one variable. And the constraint, this is what's called the constraint, will help you with that. And then, of course, you also need to consider your endpoints, because possibly, probably not, but possibly the maximum or minimum could occur at the endpoints. And if we were looking at the minimum, obviously the minimum would be at the endpoints, but not really too much mystery there in how you minimize x squared times y. All right, so here's another example. So we're essentially looking at a fenced area. So we have this fenced area with dividers. We have 3 sections, and we have 1,056 meters of fencing. We want to maximize the area. So area of a rectangle, of course, length times width, we'll call it xy. So we'll call each of these lengths, because each of these lines represent fence. Actually, I did that backwards, but it doesn't matter. Obviously, x should be horizontal, but that's okay. Doesn't matter that much. Now, we have a constraint. So we always, obviously, if we're just maximizing the product of two numbers, there's no maximum value because it'll just go forever. So we have this constraint. We only have so much fencing. So how much fencing do we have? We have 4 x's, 4 x lengths, 2 y lengths. So let's call this 4x plus 2y, and that's all our fencing. That equals 1,056. All right, same procedure. Let's solve this for one of the variables. In this case, neither one of them were squared, so it doesn't really matter which one you pick. We'll just choose y. So let's solve this for y. And we get y equals negative 2x plus 528. Then we'll substitute. We get x times negative 2x plus 528. So the area is negative 2x squared plus 528x. What do we do next? Take the derivative, of course. A prime is going to be negative 4x plus 528. Set that equal to 0. And so we get that x is 132. And if x is 132, y is negative 2 times 132 plus 528. Oops, don't need that. And so y is going to be 264. Then, what is our area? So I guess we could also talk about what's the domain. So obviously, if x is 0, then we don't really have any area. If y is 0, then we don't have any area. So really, this has to be the maximum, because either we have x equals 0 and y would equal, what is that, 528? Or we have y is 0 and x is 132. No, 264. But in either case, I mean, it doesn't really matter what x is. If the area of this rectangle would be 0, the area of this rectangle would be 0. So those aren't really a consideration, although they are the endpoints. So the maximum area would be 132 times 264, which is 34,848. All right, so same process, setting up. We want find an equation for what we want to maximize or minimize. we find an equation or a function for the constraint. So if we're maximizing something, we can only go up so big, or the problem is pointless. If we're minimizing something, we can only go so small, or else the problem is pointless. All right, so one more. We have a disease, follow percentage of the population infected T days after the disease arrives is given by this function. T is between 0 and 50, and we'll just kind of do both these together. And this one, we don't really have a constraint. T provides its own constraint. So we just need to take the derivative. So we'll use the product rule. So we have 7e to the negative t over 10 minus 7 tenths te to the negative t over 10. Set it equal to 0. Let's factor out 7e to the negative t over 10. We're left with 1 minus 1 tenth t. Set that equal to 0. Divide this out, and we get t equals 10. So, considering the endpoints, and this time maybe you do, or you always, I guess, need to. Possibly it's relevant here. So t is between 0 and 50. T equals 10 is a critical point. So let's find p of 0, p of 10, and p of 50. So p of 0 is just going to be 0. Obviously, on day 0, there nobody's infected. P of 10, plug that in the calculator, and we get 25.75. This is 25.75%. And then P of 50, plug that in the calculator, and we will get 2.358%. So here is our maximum. Okay, so no big deal, especially with this one, no big deal. So the big party, I guess, is learning how to write these constraints, getting your function that you can maximize or minimize, and you just take the derivative, do what we did in the last section.